Question 4 is about the photoelectric effect. State what is meant by the threshold frequency of the incident light. That's something you should have learned. Whenever it says state what's meant by something, that means that you've been told what it means. It's in the book. It's a matter of learning it. So no point me telling you now. I can tell you it's on page 30 of your book. I can also tell you that if you wanted a more concise definition, it's in the glossary, the back of the book, threshold frequency. A part 2, explain why the photoelectric effect is not observed below the threshold frequency. And again, that explanation is in your book. This is all about energy. The photon brings energy in, the electron requires energy, and the explanation hinges around whether or not the photon brings in enough energy. It's in your book. Make sure your explanation makes it clear whether you're talking about the photon or the electron. If you just use the expression it, it's going to be really confusing. So you might think you know what you're saying if you say it doesn't happen unless it has enough energy to give to it. But to an examiner that would be totally meaningless. So make it clear what brings the energy in, what requires the energy, and then use any technical terms that you know about how much energy the electron does require to leave the surface. Part B is a calculation. So it tells you you've got light of a certain wavelength and it asks you to find the energy of a single photon. Well, hopefully we remember it, but if we don't, we look at the datasheet. And it tells us here the photon energy, E equals HF, which is the form we normally learn it as, but then it does tell you the other form, HC divided by lambda. So if you're told what the wavelength is, you don't need to work out the frequency, because it tells you the formula here. So you can find out the energy. So we work out how much energy the photon has. Calculate the maximum kinetic energy of an electron emitted from the surface. So we have to think what's going on. The photon brings a certain amount of energy. It tells you that the metal's got a work function of 1.4 times 10 to the minus 19 joules. Remember what work function means. That's the energy an electron must be given in order to escape from the surface. So the answer you get here is how much energy the photon brings. That's how much energy it requires for the electron to leave the surface. So hopefully this answer will be bigger than that value, 1.4 times 10 to the minus 19, otherwise they wouldn't get any effect. How much bigger? You can work that out by doing the subtraction, and that's the energy that's left over. And the question is, what's the maximum kinetic energy? Well, isn't that the energy that's left over when the photon has provided the energy to provide the work function? So you should be able to do that one quite straightforwardly. B part 3, calculate the maximum speed of the emitted electron. So we've just worked out the maximum kinetic energy an electron can have, and the electron that's got the maximum kinetic energy will also have the maximum speed. So we need to know the formula that links speed and kinetic energy. And if you look at the data sheet, there's a formula here. EK, kinetic energy, is a half mv squared. So there's the formula. I'm not going to do the calculation for you, there'll be no point in that. The kinetic energy is the value that you've already calculated. What I'm going to do is I'm going to give an example now using a different number. So the kinetic energy for the previous question, the answer is not this, but this is how you would do it. In my example, I'm going to say that the kinetic energy of the fastest electrons is 4 times 10 to the minus 19 joules. That's just a number I've made up, just to show you the method. You've got to work with the numbers that you get from that answer. So we've got half mv squared equals 4.0 times 10 to the minus 19 joules. What is m? Well, it's an electron we're dealing with. So a half times, look on the data sheet, the mass of an electron, 9.11 times 10 to the minus 31 kilograms. So a half times 9.11 times 10 to the minus 31 equals 4 times 10 to the minus 19. Remember, your energy won't be that, I made this up. Oops, and I've missed out v squared, haven't I? Schoolboy error there, v squared. So now, if I multiply 9.11 to 10 to the minus 31 by half, I take it onto the other side, I can get left with v squared equals 4 times 10 to the minus 19 divided by 0.5 times 9.11 times 10 to the minus 31. I probably wouldn't bother writing that down for real, I'd just put it on the calculator. 4 times 10 to the minus 19 divided by, and to avoid mistakes let's put a bracket, 0.5 times 9.11 times 10 to the minus 31, and I get 8.78 times 10 to the 11, that's v squared, so v equals the square root of that. Which we get the calculator to put in standard form, or 9.4 times 10 to the 5 metres per second. And that seems a good sort of speed to get for an electron, because it is very fast, but it's nowhere near the speed of light. So that's the method that you use, except of course you use the proper value for kinetic energy, not the one I just made up. And the last part, calculate the de Broglie wavelength of the fastest electrons. And the fastest electrons must be the ones with maximum speed, which is these, which is the ones with maximum kinetic energy. So it's all the ones we've been working with. And the datasheet doesn't just tell you the de Broglie wavelength, it tells you that it is the de Broglie wavelength, which is rather helpful. So the wavelength is h over momentum, which is h over mv. So if we just worked out the speed, we know the mass of an electron. H, of course, is Planck constant we've been using, which is on the data sheet, so we can work out the de Broglie wavelength.